Okay, today we're going to spend a little bit of time reviewing for our test tomorrow. This first lesson we looked at was called Points, Lines, and Planes and Their Attributes. If you remember, this is the one that was really, really long. It was the first night of notes that you had to take. I should have broken it into two halves instead of giving you it all in one night. And actually, the lessons that you're getting ready to flip back through here, I did break them into two halves, but it may be all in one piece in your notes. But follow along with your notes, highlight anything, star anything, underline anything that you need to work on or understand better or come ask questions on, stuff like that. Come on, computer, keep up. Okay. The objective was the student will discern the differences between Euclidean and non-Euclidean geometries and learn the basic geometric structures. First thing we did was we talked about kind of the construct of this class. It was put together by a Greek mathematician. His name was Euclid. This was around the 3rd century. There was a lot of people working on geometry. Euclid kind of pooled all the information together, kind of gave it some uniform language and stuff like that. And he composed several textbooks which were titled The Elements. Okay, Euclid's definitions and theories and all that pretty much stood pretty solid all the way up until about the 1800s. Okay, now Euclid's structure, and we didn't really talk about this much in the beginning, Euclid's ideas were based upon what we call defined terms and undefined terms. Now it may sound a little bit like those are antonyms of each other, defined and undefined, and you're kind of right. Okay, but more specifically, what we're talking about when we say a defined term is something that comes with an elaborate definition, something that has to be spelled out word for word in order for us to understand it. Okay, those things are stuff like definitions. We've seen plenty of definitions, and also theorems. Okay, one you're probably already familiar with is the Pythagorean theorem. Pythagorean theorem takes great care to describe that in a right triangle with legs of A and B and a hypotenuse of C, that A squared plus B squared will always equal C squared. Okay, that is a defined term because it has been spelled out to the point where anybody can work through it. Anybody can comprehend it based upon the explanation. Okay, so what is an undefined term? Well, we actually tinkered a little bit with undefined terms the other day when we were talking about reasoning, going through the inductive and deductive reasoning. Some people said that that was common sense, some of the deductive reasoning things. And you're right, it is what we kind of think of as common sense, but those are undefined terms. Okay, so like some of these definitions where we've been saying, you know, like when two lines intersect each other. Okay, what is the intersection when two lines intersect each other? It is a single point. Okay, it's just a single point where they cross. That's not a defined term. Nobody actually went through and spelled out a big mathematical definition to prove that that works or anything like that. It is simply common sense. If two lines are going to run across each other, they have no choice except for to only form a single point. It's undefined because that's the only way it can work. Okay, so that's what Euclid was about, defined and undefined terms. And, you know, Euclid's idea of geometry was kind of like in a perfect world. On paper, here's the way things would work. Okay, so like that left-hand diagram there, in the world according to Euclid, the shortest distance between 2 points is a straight line. Okay, well, around the 1800s, people started to do a little bit better thinking than Euclid was doing at the time, and we started to realize, you know what, how about this? I mean, if you were to say, okay, how far is it from Odessa, Texas to China? Okay, well, how do you connect those 2 points? Do you just go a straight line through the center of the earth? Well, that's kind of you know, impossible and impractical. Okay, so we have to understand that Euclid's ideas were solid, and that's what this class is based upon. Okay, but his ideas don't always translate exactly the way they should into the real physical world around us. And so this new thinking of this new translation is what we call non-Euclidean geometry. Okay, Euclid's right. The shortest distance between 2 points is a straight line. Okay, but in the real world, the shortest distance between 2 points is the shortest, or the short, the okay, the not a straight line, but the straightest possible line. that we may not always be able to go directly from point A to point B. Like the taxi cab geometry, it may be necessary to turn corners to get from where we were to where we were trying to get. Distance from here to China. It may be an arc traveling around the outside of the planet because we can't go directly through the planet. Okay, so that's kind of the difference between Euclidean and non-Euclidean. Okay, but back to Euclid. Okay, Euclid's ideas, he broke everything down into three basic constructs. Okay, the points and the lines and the planes, and he concluded that everything in geometry can be built out of these three items: points and lines and planes. Okay, points, they are the most basic definition in Euclid's little world in zero-dimensional space. Okay, zero dimensions. What does that mean? It means they have no width, they have no length, they have no depth. In fact, when you think about a point, okay, that is something that we cannot even visually comprehend. Our three-dimensional eyes and brain cannot see a point because it doesn't have any volume to it. Okay, has no width and no length and no depth. It does not exist to us in three dimensions, but we understand the concept of it. Okay, just like everything else in geometry, when we go to name something, we call it by whatever the name of the structure is: point this, line segment that, ray whatever. Okay, we name what kind of an item it is. And when it comes down to points, points are simply a single capital letter. So in this case, point P. Okay, a line was Euclid's most basic structure in two-dimensional space. Okay, and it's in one-dimensional space. It's in one dimension because a line has length, but it has no width and it has no depth. So again, this would be something that would be impossible for us to see in three dimensions because again, it has no volume. It has to have some volume for us to be able to see it. Okay, but we understand its concepts. We need at least 2 points in order to construct a line. Okay, it can take more points than that. We can have more points than that. Okay, but all we need is 2. Okay, we have a little notation for lines. Okay, right there, the little arrow line with the double arrows on the top of it to signify line, because lines go on forever in both directions. Okay, and if you have more than 2 points on the line, it's fine. You only need 2. The most proper way is to pick on the outside 2. So if you have a whole alphabet going across your line A, B, C, D, all the way up to Z, then they're probably going to call it line A, Z. Pick on those 2 outer points, and that's how they'll name it. Another definition there: if 2 or more things were to exist on the same line, they would be collinear. The prefix co means of the same, and of course line, linear is for line. Ray, if you take a line and force it to have an end point rather than one of its sides going off infinitely, that would be a ray. Okay, so we have a little notation for ray, a little symbol. There it is. Okay, you see it's missing one of its arrows now. It has an end point, travels the opposite direction. Okay, and when it comes to naming rays, remember that you have to get the order correct. The endpoint comes first, and then whatever side travels on infinitely goes next. Okay, have to get the endpoint name correctly. For example, this green one here in the middle, if you call it ray AB, you're exactly right. A is the endpoint, B is the side that travels on infinitely. If you call it ray BA, you're incorrect, okay, because you listed the wrong endpoint. So make sure we get that. And opposite rays, okay, rays that are opposite simply begin at a common endpoint, head exactly in the opposite direction from each other. Line segment is a line that does not continue infinitely in either direction. Okay, so we end up with 2 endpoints in the case of a line segment, and you can name it either direction, line A or line segment AB or line segment BA, but it is slightly better to get it in alphabetical order, so line segment AB. If we run across the situation where we have 2 points or 2 letters listed back to back like we have here, but no marker over the top of them, no line symbol, no ray symbol, no line segment symbol, this is referring to a distance or a length of whatever it is that's connecting point A and point B. Okay, Euclid's last structure is the plane. Planes exist in two-dimensional space, meaning they have length and they have width, but they have no depth. Okay, this is closer to the real world for us than any other thing, because we can understand a surface. Okay, but again, we can't actually see a plane in the real world because it has no depth. If it has no depth, it has no volume, because volume is three-dimensional, and we cannot see that with our eyes. Okay, but anyway, the other thing here is when you name planes, there's a couple of different ways to name planes. One of them being the three-point method for planes, where it says you need to name three non-collinear points in order to name a plane, and the other one is sometimes they can give you a name like this little P floating inside there in one of the inner corners, okay, that we can call it. Now, one of the things we never really did talk about, but we're going to mention it now, is the definition said when you go to name a plane that the 3 points you name it need to be non-collinear, so not in a straight line. Okay, so let's think about this for a second and see if we can't figure out why that would need to be. Let's say we have 3 points. I'm going to say point X, Y, and Z, and I'm going to put them up here at the front of the room, down here at the floor in the front wall. So I'm going to put point X right here. A few feet over, I'm going to put point Y, and a few feet over, I'm going to put point Z. Okay, they are collinear, right? All in a line together. They are collinear. So why on earth is this such a problem? Why can't we name a plane? Let's say we're trying to name the front wall here. Okay, does the front wall hit point X and point Y and point Z down there at the bottom? Sure it does. Okay, so why can't we just say that, hey, those 3 points can be this plane, that they can represent the front wall? Okay, what's wrong with that? The question is, or the issue is that the only plane that can run into those 3 points? Well, what about the floor of the room? Does the floor of the room hit point X, point Y, and point Z also? It does. And we could bring another plane, here in the space with us and kind of bring it down, pass it through that seam down there at the bottom. So we can actually start creating a whole bunch of planes that could all intersect those 3 points. Okay, so just like we came up with the 3-point naming system for angles, we did that so that we wouldn't get confused over which angle is actually being talked about in a diagram. And if we pick 3 points that are in a straight line to name a plane, then we are no longer sure about what plane is actually being talked about. But let's say we take point Y off the floor down here and put it up here on the wall by the overhead screen. Okay, so now you got point X down by the floor, you got point Y way up here on the wall, and point Z down by the floor. That is still the front wall, right? All 3 points are in the front wall. Is there any other plane that can make contact with all 3 of those points at the same time? And it can't, okay? Because now when they're not collinear, now there's only one plane that can make contact with all 3 of them. Okay, that's why we insist that they not be in a straight line, so it doesn't generate any confusion about which plane a problem might be talking about. And down there at the bottom, if 2 or more things exist in the same plane, such as points A, B, and C up above, that would be coplanar. Okay, so at that point in time, that's where I shut off the notes for next year. Okay, but y'all were still going, still had a little bit more information coming, and I apologize for the notes being as long as they were. So let's see if we can't take a look at the remaining definitions. The objective was still the same. Parallel lines. We threw away an old definition of parallel, okay, from junior high. Back in the day, they told you that parallel means they don't intersect. Okay? Well, the ruler in my hand and the clock on the wall back there do not intersect. Does that mean that they're parallel to each other? No, that doesn't even make any sense. Okay, so the old definition we had of just saying 2 things don't intersect and that makes them parallel, that's really badly incomplete. Okay, the real definition does say that they can't intersect, but they also have to be in the same plane with each other. Okay, because if I hold these 2 rulers up like this, okay, they're not intersecting. Are they parallel to each other? Clearly not. But if we force them into the same plane with each other and they don't intersect, now they are parallel. Okay. We said there's a few different ways that we will be able to spot parallel lines in a diagram. Okay, they might put little triangles in the body of the lines to show us parallel. They might put little arrows in the body of the lines to show us parallel. They might give us external information about the lines to tell us that they're parallel. The third way is going to be one of the ways we're going to spend a good bit of time on this year. There may be some mathematical information going on, okay, some angles that are attached to our lines that will tell us that they're parallel, and that's one of the ways we're going to be working on. And the last thing we said about parallel was to remember that lines are never ever in geometry going to be parallel because they look like it. Okay, and unfortunately, it's not just to be difficult on you. It's because the human brain, when we look at angles on paper, our brains cannot tell the difference between an angle and another angle that's off by 1 degree either direction. Okay, our eyes and our brains are just not attuned enough to be able to measure that mentally. Okay, so if we can't tell the difference in an entire degree one way or the other, we stand no chance of being able to tell if things are off by fractions of degrees, and that's going to be the case sometimes. So we will never ever decide that two lines are going to be parallel just because they look like it or just because you think so. There had better be good information, either the arrows and the triangles, or so they told us, or we've got some math and we verified it. Okay. Skew lines. Okay, a moment ago I asked you what was these. Said here's two lines, and they are definitely not parallel. These are skew. They are skew because they are not in the same plane and they do not intersect. Okay. Um, what else? Here were some of these things, some of these undefined terms. Okay, when two lines intersect, they're going to intersect to form a point. It's the only thing possible. If a line passes through a plane, it's going to intersect at a point. It's the only thing possible. Okay, and if two planes intersect, like the floor of the room and the front wall of the room, the intersection is going to be a line. It's the only thing possible. Okay, and that took care of the beginning vocabulary. From there on, we went to segments and their measures, working with angles, and then also the topic of bisecting and all of that. Okay, the student will be able to solve problems involving bisectors and midpoints. This actually proved to be a pretty easy section once you got to the math, okay, because there was a lot of vocabulary that was basically synonyms with each other. Bisecting, midpoint, equidistant. It all basically did the exact same stuff. It established that there was something exactly in the middle, and that meant that we were chopped in half on either side of it. Okay, so we came up with a definition of congruent. Congruent simply means equal measure. Okay, we came up with a new symbol for congruent. We're going to use it tons and tons this year, an equal sign with a little squiggle over the top of it. Okay, we said that in diagrams we may see things that are called tick marks. They're little hash marks that show up in the body of the line, and they mean that those two line segments are congruent. Okay, we saw an angle for the first time. An angle is when you have two rays from a common end point. That common end point is called the vertex. Okay, and there's going to be a couple of different ways that we're going to get to name our angles. First, but not very often, it's possible that they may give us a little numerical name down in there that we can call it angle 1, angle 2, stuff like that. And that's going to be convenient, especially when we end up with diagrams that have 8, 10, 12 angles in them. Sure is a lot easier to call them by a numerical name if we have them, but more times than not, we end up having to do the 3-point naming system. Okay, and again, we use the 3-point naming system in order to avoid any possible confusion. So when we say angle E, we know exactly where, exactly which angle it's talking about, not just several angles around it. Okay, so here on the left, angle DEF is one of the possible ways of naming it. Angle FED is another way of naming it. The thing you got to remember with naming angles is that it takes 3 points. The second one is the vertex. Okay, just like the vertex is kind of caught in the middle of the angle, when you name it, the vertex is going to show up in the middle of the name. Angle ZYX, angle XYZ. Any other combinations of those names is incorrect. Okay, the idea of midpoint, of course, the midpoint is exactly in the middle. Bisected, the prefix bi means two. Sected means cut into pieces, so cut into pieces 2 times. Okay, and equidistant, if you have a midpoint or a bisector, then it is equidistant out to the endpoints. So a lot of synonyms going on in there, and from that point it was a matter of putting it into problems. Okay, a lot of what we're going to be doing in geometry this year is going to be writing an equation so we can solve for a variable. Okay, and things like midpoint and bisected and stuff like that, these are definitions that are going to lead us to how do you write these equations. To write an equation, we have to be able to say that something is equal to something else. In the case of a midpoint, it may mean that one thing is exactly equal to the side across from it. Okay, but we've already seen some other topics where it might not be the case. We may not have just two things equal to each other. We may have a couple of things that are adding up to equal something. Okay, like the definition of complementary. Two things that add together to be 90 degrees. If we see that in a picture, we get one angle plus another angle that would equal 90 degrees. It just depends on what's happening in the problem. Okay, but that's what our goal is going to be, is to write those equations as the year goes on. Okay, the next one we looked at was types of angles. About half of this was entirely junior high type review. The other half was more new to us. The student will remaster the different types of angles and discover various types of paired angles. Okay, from the beginning here, back to like 6th grade or so, acute angles measure from 0 to 90 degrees. Right angles measure exactly 90 degrees. They might put the little square box down near the vertex to show us that we have a right angle. It might be there, it might not. Okay, and obtuse of angle measures from 90 to 180, and then on a straight angle it measures exactly 180 degrees. That should have been entirely review. Now we get a few new things here. Adjacent angles is one we probably need to pay some attention to. Adjacent angles is just two angles that share a side. They don't have any other special properties or anything like that. They just have a leg in common. If two lines raised or line segments intersect to form a right angle, that's what we call perpendicular. You should know that one from before. We had a new little symbol for perpendiculars, this upside down capital T down there at the bottom. Okay, linear pair, also adjacent. They do share a leg, but what makes them a linear pair is what's happening with the other sets of legs. And a linear pair, that other set of legs is going to form a straight angle. And we had vertical angles, and this is one that's missed a bunch because people know what the word vertical means in the English language, but in geometry it means something different. Okay, in geometry, vertical happens when you get a couple of lines intersect. Vertical means across from each other. Okay, so in this diagram, angle 1 and angle 4 are vertical angles. Angle 2 and angle 3 are vertical angles. Okay, and there's a basic rule that vertical angles are always going to be congruent to each other. So 1 and 4 are going to measure the same. 2 and 3 are going to measure the same. Complementary and supplementary should be reviewed from junior high. Complementary means they add up to be 90. Supplementary means they add up to be 180. Okay, rest of it was just examples. Then we started looking at some kind of methodology of thinking. We talked about reasoning a good bit. Okay, the student will discover the similarities and differences between inductive and deductive reasoning. Okay, inductive reasoning. Okay, inductive, you're just going to have to memorize this along with a lot of other things that you've got to study in geometry so far this year. But inductive reasoning is when we make predictions based upon observable patterns. Okay, predictions based upon patterns. Now, these predictions that we make are what we call conjectures. Conjectures are statements that we believe to be the truth. Okay, so we believe them to be the truth, but if there is any situation that can be come up with that goes against the conjecture, then that's what we call a counterexample or a non-example. Okay, a counterexample would make the conjecture entirely false, which would mean it's no good. Okay, we did some examples. Okay, we saw conditional form for the first time. Conditional form says if P, then Q. Okay, where P, the information about P, is the hypothesis. This is the observation, the thing that we are noticing. Okay, and then Q is your conclusion. That is your prediction or your summary that you are stating based upon your observation. Okay, and the last thing in this one was the topic of deductive reasoning. While inductive reasoning was predictions based on patterns, deductive reasoning is predictions based upon other factual information, facts based upon facts. And that's what some of you wanted to call common sense. And in a way, it is kind of common sense because you have to know something about what was said in order to be able to make a connection in the deductive reasoning. And on the assignment that you had, some of you had some trouble keeping it straight, which one was inductive, which one was deductive. So we probably need to spend some time working on that before tomorrow gets here. Okay, that was the end of the reasoning, and the final lesson was on negations. Okay, and negations deal with what we can do with the conditional statements. Student will discover the meanings of the negations and apply them to provided conjectures. Okay, you have the conditional statement, if P, then Q, where P is the hypothesis and Q is the conclusion. Okay, one of the things that can be done to a conditional statement is its converse. Okay, and what a converse does is it takes the hypothesis and conclusion, the P and the Q, and it switches their positioning in the sentence. So instead of saying if P is true, then Q will happen. Okay, the converse will say if Q is true, then P will happen. So the hypothesis and the conclusion are flip-flopped with each other. Another one of the negations is called an inverse. An inverse basically reverses the meaning of what was said in the statement to begin with. So if you have if P, then Q, P and Q aren't going anywhere, but we're going to reverse their meanings, and that typically happens by adding in words like not or except or things like that. So instead of if P, then Q, we end up with if not P, then not Q. And if you can remember converse and inverse, then you've pretty much got contrapositive because it does both of them at the same time. It's going to reverse the hypothesis and the conclusion, and it's going to negate them. So instead of if P, then Q, you end up with if not Q, then not P. And as always is the case with the converse and the inverse and the contrapositive, after you write them, you have to kind of read them and think about them to decide if they are still actually true or not. Okay, sometimes they will be entirely true, sometimes they'll only be partially true, sometimes they won't be true at all. It just depends upon the statement that you started off with, and that should be the end of all of that. So that's the material that you have for the test tomorrow. Obviously, it's not a whole lot of mathematical ability at this point. Like we said, we're not learning a whole lot of new math and geometry. We're learning new concepts, and that's going to mean we're going to need to spend some time just flat studying. So you probably need to get yourself organized in such a way, however it is you study for, biology vocabulary tests or English vocabulary tests or the periodic table in science, okay, flashcards, I don't know how you do it, but however you do it, that probably needs to happen because you don't stand a chance on the test tomorrow if you're not going to understand the vocabulary that the test is going to be written in. So make sure you pay good attention to your vocabulary, and good luck on the test.